So you got very close to the answer in this, but it did require an additional consideration. As I'm not sure whether or not you're learning about Bayesian probability in your class, this would be something where this would apply, but I will answer this without the equation for Bayesian probabilities, just in case you're not familiar with that equation. Okay, so as far as this woman goes, so 26-year-old woman of Norwegian descent seeks genetic counseling. Her brother died at age 8 of documented cystic fibrosis, and both of the parents are deceased. So we know that the brother has cystic fibrosis, which means they are homozygous recessive for those alleles. And that means that both of her parents had to have been carriers of that cystic fibrosis allele. Okay, so the woman undergoes DNA testing for 70 CF mutations, which collectively detects approximately 90% of CF carriers of Northern European descent. Okay, so you know that this woman could either be homozygous dominant and healthy, or heterozygous and being a carrier of the cystic fibrosis mutated allele. Okay, so the testing reveals that she is negative for all 70 mutations. So what is the probability that she is a heterozygous carrier of cystic fibrosis? Okay, so you did the first part correct. So I won't go over the details of the understanding of how to get that 2/3 and 1/3 probability. So we know that she will either be heterozygous. She has a 2/3 probability of being heterozygous. So I'm going to use the letter C for the alleles, capital C, lowercase c for probability of being heterozygous, or a 1/3 probability of being homozygous dominant. Okay, so we know that those are the two possible genotypes that she could have. So we have another consideration. We have to consider the likelihood of testing positive or negative for each of these genotypes. Okay, so first, if an individual is heterozygous, that test will detect approximately 90% of the CF carriers. Okay, so 90%, I'm going to use fractions. I like using fractions a little bit better, so I'm going to continue to use fractions. So 90% would be 9 out of 10 are going to test positive. Okay, so I'm going to put a plus here for testing positive. Okay, which means that the other 1 out of 10, the other 10% of individuals will test negative if they are heterozygous, if they are carriers. Okay, now we do also need to consider the other genotype being homozygous dominant. Okay, so homozygous dominant individuals, if they get tested, assuming there's no sort of false positive probability going on, if they are tested, they will test negative because they do not have that mutated allele. And so all of individuals who are homozygous dominant will test negative. And so I'm going to use the letter or the number 1 representing 100%, or all of these individuals will test negative for this test. Okay, so now we can just multiply out each of these different probabilities, 2/3 times 9/10. Because our second probability here is going to leave us in 15ths, the 2/3 times 1/10 is going to leave us in 15ths. I'm going to make sure this stays in 15ths. And so let's see, so I'm going to multiply this out, simplify that a little bit. So this is going to give us 9/15 for individuals who are, so 9/15 for individuals who are heterozygous and test positive for this test. Okay. In our next category here, we have 2/3 times 1/10. 1/10. So again, I'm going to simplify this. That's going to give us 1/15. So this is the number that you calculated before. So 1 out of 15 likelihood of being heterozygous and testing negative. Okay. And then our last example here, homozygous dominant individuals, 1/3 times 1 is going to be 1/3. And if we put that into 15ths, that's going to be 5/15. And so we have 5 out of 15 likelihood of being homozygous dominant, and therefore they would test negative. Okay, so we can always double check this. Total of the probabilities, so 9 out of 15, so 9 plus 1 plus 5 is going to be 15 out of 15, so those are all of our probabilities, all of the possibilities. But this, we have an additional piece of information that we need in order to answer this question. The additional piece of information is the fact that she is known to have tested negative, which means that she is absolutely not part of this top group, this 9 out of 15 that tested positive. She is only one of these individuals. And so we have to take into consideration that she has tested negative. So she is not part of that 9 out of 15. She is some percentage of these individuals who tested negative. So the total for the individuals who test negative is going to be 1/15 plus 5/15, or 6/15. So this is the total amount of the individuals who tested negative. Therefore, the likelihood that she is a heterozygous carrier that tests negative would be 1 out of 15 for this 1 out of 15's heterozygous testing negative over the total of the possibilities of the individuals who test negative, which is 6/15. 6/15 test negative. And so when you simplify this, 1/15 over 6/15 is the same as 1/6, and that is the answer. Okay? Does that make sense?